Welcome to this deep dive. Today we're getting into the nuts and bolts of modern NVIDIA GPU cores.
It's a fascinating area, especially because getting detailed info is uh, usually quite tough.
Right, so we're drawing heavily on that paper, Analyzing Modern NVIDIA GPU Cores by Huerta and the team.
We are. Their work gives us a rare look under the hood.
And our mission here is really to pull out those key architectural bits, the design choices that matter for performance and efficiency. Basically, giving you the key insights without needing to wade through all the dense technical details yourself.
Exactly. Because as I mentioned, understanding these modern microarchitectures is a real challenge. There's very little public documentation.
And academic research often uses older models.
Often, yeah. You still see studies based on, say, the Tesla architecture from 2006, which is, well, it's very different from what's in GPUs today.
So how did these researchers get around that lack of information? Sounds like quite a task.
It involved a lot of clever reverse engineering, primarily using micro-benchmarking.
Micro-benchmarking. So like running tiny specific tests.
Precisely. They create very small code sequences, targeting individual instructions or features. Then they measure the execution time super accurately using the GPU's own clock counter.
Okay. And they use tools to directly mess with the assembly code.
Yes. Tools like CU Assembler let them manipulate the low-level SAS instructions directly. This gives them fine-grained control to test specific hypotheses about how the hardware behaves.
Can you walk us through an example? How did this method reveal something concrete?
Sure. Take register file bank conflicts. That's a classic GPU performance issue.
Right, where multiple parts of the code try to access the same memory bank in the register file at once.
Exactly. So they wrote code sequences, as shown in listing 1 in their paper, where they carefully controlled which registers were accessed by consecutive instructions.
And by changing the registers.
They observed tiny differences in execution cycles. If 2 instructions needed the same bank, it took longer. This allowed them to map out the banking structure and, quantify the performance hit of these conflicts.
Makes sense, like finding traffic jams on the internal data highways.
A good analogy, yes.
Now, one of the big takeaways seemed to be a shift in handling data dependencies, making sure instructions get the right data at the right time. How has that changed?
It's a major shift. Older GPUs often used hardware scoreboards, basically dedicated hardware tracking dependencies at runtime.
Okay, like an air traffic controller for data?
Sort of, but modern NVIDIA GPUs, the ones they studied, rely much more heavily on the compiler.
The compiler. So the software is telling the hardware how to manage dependencies.
In essence, yes. The compiler embeds control bits directly into each instruction. These bits guide the hardware on register usage and timing, preventing data hazards. It's really a hardware compiler co-design approach.
Interesting. How does that work for simple instructions, the ones with predictable timing?
For those, the fixed latency ones, the compiler uses something called a stall counter. It's associated with each warp, a group of threads executing together.
And the compiler sets this counter
based on the known latency of the instruction producing the data. Let's say an instruction takes 5 cycles. The compiler sets the stall counter for that warp, and the hardware won't issue the dependent instruction until that counter clears.
So it prevents the next instruction from reading the result too early, a read after write, or raw hazard.
Correct. And the benefit is you need less complex hardware for runtime checking, which saves chip area and energy.
What about the yield bit? What role does that play?
The yield bit is another compiler control. It basically instructs the hardware not to issue another instruction from that same warp in the very next cycle.
So it forces a one-cycle pause for that specific warp.
Yes. If other warps aren't ready, it might introduce a bubble, but it gives the compiler a way to manage pipeline flow or resource usage explicitly.
Okay, but not all instructions have fixed latencies, right? Memory access, special math functions, those can vary.
Right. And for those variable latency instructions, the system uses dependence counters. These are special registers labeled SB0 through SB5 in the paper. Each warp gets 6 of them.
6 counters per warp? How do they work?
When a variable latency instruction that produces a result is issued, the compiler designates one of these SB counters. The hardware increments it.
Okay.
Then, when the result is ready, the hardware decrements it. An instruction that consumes that result is programmed by the compiler to wait until that specific SB counter goes back to 0 before it can execute.
So it's like a little flag system managed by the compiler through these counters.
Pretty much. It handles both raw hazards reading too early and also right after read war hazards, where an instruction might overwrite a register before a previous instruction has finished reading it.
The paper has that figure 2 example with loads and an add. Can you elaborate on how the SB counters work there?
Sure. In that figure, you have an addition that needs results from two prior load instructions. Let's say the compiler assigns SB3 to track these loads. SB3 gets incremented when the loads issue, and it only gets decremented when the data from both loads is written back to the registers. The addition instruction is set up to only proceed when SB3 is 0, ensuring it gets the correct loaded data.
And it could also handle war hazards.
Yes. If, say, the addition writes to a register that a later load instruction needs to read first, another counter, maybe SB0, could be used. The later load increments SB0, and the addition decrements it only after it has read the original value. The addition would then wait for both SB0 and SB3 to be 0.
So the instruction itself encodes which counters it needs to check.
Exactly. It has a dependence mask specifying the relevant SB counters.
What about that dep-bar-daily instruction they mentioned? Sounds like more fine-grained control.
It is. Dep-bar stands for dependence barrier. Dep-bar lets the compiler insert a wait instruction that checks if a counter is less than or equal to a certain value, or it can wait for multiple counters to all hit 0 simultaneously.
So more complex synchronization.
Yes. Useful for waiting on a whole sequence of variable latency operations, or maybe reusing a single SB counter cleverly for different hazard types across a block of code.
And there's also a reuse bit for the register file cache, more compiler hints.
Correct. Another bit set by the compiler, this time per source operand. It signals to the hardware, hey, this register's value might be needed again soon, consider caching it.
So the register file cache is also software managed, essentially.
To a large extent, yes. The compiler drives the caching decision.
It's really striking how much intelligence is pushed to the compiler. How does this compare to, say, AMD's approach? The paper touches on that briefly.
AMD also uses a co-design, but it's a bit different. They have a wait-sent instruction.
Wait.
Yeah, it explicitly tells the hardware to wait until specific types of operations, like memory ops or ALU ops, have completed, checking dedicated hardware counters. Unlike NVIDIA's SB bits within the instruction, AMD uses a separate instruction for the wait.
So potentially more instructions overall for AMD.
Potentially, yes, but it might simplify the instruction decoding logic in the hardware. NVIDIA's approach integrates the wait condition into the instruction itself, which could allow for finer control, maybe better latency hiding, but puts more burden on the compiler to get stall counts right for fixed latency stuff. Trade-offs, as always.
Okay, let's shift gears to the core itself. The issue scheduler, the part that decides which warp runs next. They called it CGGT2Y.
Right, CGGT2Y, compiler-guided greedy, then youngest.
Catchy. What determines if a warp is even eligible to run?
Three main things. First, it needs a valid instruction ready. Second, no data dependencies with older, still-in-flight instructions from the same warp. Third, for fixed latency instructions, the necessary execution resources must be free.
And the CGGTY policy itself, how does it choose?
It's greedy first. If the warp that just executed can issue another instruction right away, meets all criteria, it gets priority. Keep the same warp going if possible.
Makes sense, maybe better locality or state reuse.
Possibly. But if the current warp can't issue, maybe it's waiting on a stall counter or a dependence counter, then the scheduler switches. And it picks the youngest warp among all the other warps that are ready to issue.
Youngest, not oldest. Why youngest?
The paper suggests this likely helps ensure forward progress for all warps, and perhaps interacts well with how resources or instruction buffers are managed. Figure 4 illustrates this.
How so? What do the scenarios in Figure 4 show?
They show, for example, how the scheduler sticks with a warp if its instructions are hot in the cache. They show how a stall counter forces a switch to another ready warp, and they show the yield bit causing a switch to the youngest ready warp, letting others run. It visualizes that greedy then youngest logic in action.
Okay, let's look at the front end, getting instructions to the scheduler, fetching. They mention 4 subcores per SM.
Yes, and warps are distributed across these subcores in a round-robin fashion. Each subcore has its own tiny L0 instruction cache.
And they share a larger L1 cache.
Right, the 4 subcores share an L1 instruction cache. The researchers also think there's likely an instruction prefetcher, probably a stream buffer, maybe holding around 16 instructions.
A stream buffer just grabbing the next sequential instruction.
That's the idea.
Yeah.
For the fetch policy itself, they propose it tries to fetch for the same warp that just issued an instruction in the previous cycle. Keep the pipeline flowing for that warp.
But what if that warp's instruction buffer is full?
Then the fetch unit switches. In mirroring the issue policy, it likely switches to fetch for the youngest warp that currently has space in its instruction buffer.
And they estimated that buffer size.
They reasoned it's likely around 3 entries per warp. This size seems to match the needs of the greedy issue policy, having a small buffer ready for the currently executing warp.
Diving deeper into the core resources, the register files, there are quite a few different types.
Yes, they identified several. Regular registers for general computation, uniform registers which hold the same value across all threads in a warp, predicate registers for conditional execution.
Uniform predicate, SB registers for those dependence counters we discussed, B registers, special registers, quite a list.
It is, and one really interesting finding was the apparent absence of a dedicated operand collector stage.
An operand collector, what's that usually do?
In some designs, it's a stage that gathers all the source operands for an instruction before it goes to the execution unit. But the researchers argue it doesn't fit well with NVIDIA's model,
Why not?
because gathering operands can take a variable amount of time, depending on where they are. That variability would clash with the whole fixed latency instruction model that relies on the compiler knowing exact timings for stall counters.
Ah, okay. So ditching the collector maintains that predictability. What about register file bandwidth? How fast can they read and write?
They measured pretty high bandwidth, about 224 bits per bank for writes, and the same for reads, 1024 bits per bank per cycle.
And reading takes a couple of pipeline stages.
Yes, they describe a two-stage read pipeline, control and allocate. The allocate stage is crucial. It reserves the physical read ports on the register file banks.
And conflicts there can cause stalls.
Definitely. If multiple instructions within or across warps need the same read port simultaneously, some will have to wait. They estimate reading operands typically takes about 3 cycles for a fixed latency instruction.
That sounds like a potential bottleneck. Which brings us back to the register file cache, the RFC. You mentioned it's compiler managed.
Right. Its main job is to reduce that read port pressure on the main register file and also save energy by avoiding reads from the larger, more power-hungry main file.
And it only caches operands from the regular register file.
Correct. Not uniform or predicate registers, just the regular ones.
How is it organized?
It seems there's one cache entry per register file bank within each subcore, and each entry is wide enough to hold 3 24-bit operand values.
3 values. Why 3?
To match the maximum number of source operands an instruction might have, like 2 inputs and a predicate.
And caching happens based on that reuse bit from the compiler.
Exactly. If the compiler sets the reuse bit for an operand, the hardware might cache it. A hit then occurs only if the next instruction using that register is from the same warp, accesses the same register ID, and needs it in the same operand slot. For example, source 1 versus source 2.
So it's quite specific conditions for a hit. Listing 2 in the paper shows examples.
Yes, listing 2 clearly demonstrates how setting or not setting the reuse bit and which operand slot is involved determines whether you get a cache hit or have to go back to the main register file.
Okay, lastly, let's touch on the memory pipeline. Moving data between the core and memory. Any key findings there?
Well, it has local stages in each subcore, then shared later stages like the L1 data cache and the shared memory interface. They estimated the load store queues buffering memory operations are about 4 entries deep per subcore.
So they can buffer a few pending memory ops.
Right, up to maybe 5 consecutive memory instructions could be buffered before stalling. They also measured the rate of requests to global memory about 1 every 2 cycles from any given subcore.
And calculating memory addresses.
That seems to have a throughput of about 1 address calculation per 4 cycles per subcore.
Table 2 listed specific latencies. Any highlights there?
Yeah, a few interesting points. Accessing global memory is faster. If you use uniform registers for the address, likely simplifies the hardware path. Shared memory loads are significantly lower latency than global memory loads, as you'd expect.
And data size matters.
Yes, the latency for hazards involving memory operations, raw war, changes depending on the size of the data being accessed.
They also mentioned different constant caches.
Right, it looks like fixed latency instructions, reading constants use one cache, L0FL, while the specific LDC instruction uses a different one, L0VL. Separate pathways for different types of constant access.
And that LDGSTS instruction.
Ah, yeah. Load global to shared. That one's neat. It loads directly from global memory into the on-chip shared memory, completely bypassing the register file. Useful for certain data patterns.
So after all this reverse engineering, did they validate their model? How accurate was it?
They did. They compared their model's predictions against real Ampere hardware and also against a CellSim, a popular academic simulator. Table 4 shows their model was significantly more accurate than a CellSim for Ampere.
And what about that instruction prefetcher analysis?
He did a sensitivity study, shown in Table 5. It suggests their hypothesized stream buffer size of 16 performs really well, almost as good as a perfect cache for many typical GPU workloads, though it was less accurate for benchmarks with lots of complex control flow.
And the register file analysis, did accurately modeling that matter much?
Table 6 shows the average performance impact across benchmarks wasn't huge, but for specific benchmarks, like some heavy math ones, Max Slops, Cutlass, getting the register file right made a big difference.
Right.
So it highlights areas where accurate modeling is critical.
They also compared their software-hardware dependency mechanism to a traditional scoreboard, right?
Yes, Table 7. The key finding there was that the control bit approach NVIDIA uses has a much lower estimated hardware area overhead compared to a traditional scoreboard while achieving similar performance accuracy.
That's a significant saving, especially as you pack more warps onto an SM, like in newer architectures.
Exactly. It implies this approach scales well. They also show their findings helped improve accuracy for the older Turing architecture too, suggesting the core principles apply across generations.
This has been a really deep dive into how these GPUs tick, thanks to the work by Huerta and colleagues.
It really underscores that tight integration, that hardware compiler co-design. It's not just fast silicon, it's smart software, enabling the hardware.
Absolutely. The complexity is immense, but the research reveals this elegant, if intricate, dance between the compiler and the chip.
The reliance on the compiler to manage hazards and resources is probably the biggest takeaway for anyone programming or analyzing these things.
So for you listening, understanding this compiler role is crucial if you want to get the most out of these incredibly powerful processors.
And it makes you wonder, doesn't it? How will this deep relationship between hardware and compiler evolve in the next generation of GPUs? What new optimization strategies might this unlock down the road?